to the shore. So by the time they brought back whatever been caught, the customers, when they eat this fish, it's no more fresh. Right? It's no more fresh. So the solution for the fishermen was they have to try how to make the fish that they caught to be fresh until they are back. So the simplest answer they thought of was to make sure they are alive, put in the tank, right, in the ship. So again, they brought back the fish. So when the customer brought and started eating the fish, again, it's not as good as when they were actually capturing or taking this fish when they were nearer to the shore. So what the Japanese then tried to solve was to introduce, if you look at this slide, a bigger fish, which is actually the fish that they want to sell. But they are actually, what I'm saying is they introduce smaller species of fish. Because in actual fact, when they were in their own environment, the fish was actually active trying to eat the smaller fish. Right? So this smaller fish become the food and makes the fish that is supposed to be sold more active, and eventually it becomes fresh. So how is it related to the multiplication tool? So it means you use fish to make it fresh. Okay? It's actually using the fish as the same species, so it's a multiplication tool. So similarly, when we look at the second example, we had this problem in Kuwait after the first war, the Iraqi invasion of Kuwait. The Kuwaiti land was actually full of these oil wells to be ablaze. So the answer to put out these oil wells that are blazing is to use fire. Fight fire with fire. So when you put this dynamite on top of the fire in the middle of the well using the robotic hand, the dynamite will explode and then it flushes out the oxygen and then basically it extinguishes the fire. So fire against fire. Use fire to fight fire. It's a unification tool, they call it. So now we relate to the vacuum, which is supposed to be the culprit for quantum computing, for example. We view it now that instead of the vacuum is the enemy, we can actually now look at it as the vacuum is the friend. So when we were talking about Einstein introducing these three basic principles of processes involving two-level atoms, for example, I've talked about the spontaneous emission, but there's also these two other possibilities. That is, one is the absorption, the other one is the stimulated emission. So the example I'm about to give you is a rather old example, because when we look at this particular process of stimulated emission, there's a difference between spontaneous and stimulated emission. Spontaneous is because of the vacuum. Stimulated because of you send in a photon, interact with the excited atom, and instead of one photon, now you have two photons, and they are now in the same direction. Here, is whatever photons that is coming out because of de-excitation due to spontaneous emission, the direction is random. So, if you are able to come up with this photon that are directed along certain direction, you can harness this property to create the laser which I'm holding, for example, coherent light. So this is actually the process of coherent light, where you make use of these two processes in particular to come out with what we call as the laser. Acronym for light amplification, stimulated emission of radiation. The idea is you actually make sure you have enough of the population excited state to be more than those in the ground state. So that's what they call it as population inversion. But how do you start? How do you first trigger the first few photons to start an avalanche of these stimulated photons which give rise to this population inversion? It has to come from the spontaneous emission. So spontaneous emission will trigger the avalanche of stimulated emission. So this is a first example how we see vacuum can be harnessed to actually do something good. And we can see today a lot of examples where it has disruptive technology with the lasers, a lot of things impacting the ICT and so on. Now, the other thing that we can do, this is what God has given us, is you look at the vacuum, you can actually squeeze the vacuum. So nothingness, darkness, but you can actually squeeze it. For example, you may want to squeeze it like at least this way. This is a normal vacuum. If you look at it, the uncertainty, like a cloud, the fluctuation. So you can actually squeeze it and the lips like that way or this way, or anything in between. Now, the direct manifestation of playing around with this, in this case, if you have a spectrum coming out from a two-level atom, and you measure the fluorescence from this two-level atom, you will see that you have a triplet. This is the famous mono spectrum. Now, to put an atom within the squeeze vacuum, you will be able to modify the mono spectrum. In this case, if you have this particular vacuum squeeze along this way, you have the middle spike going higher than the normal one. If you actually squeeze it this way, you have a different shape of spectrum. So why are we so interested about spectrum? I mean, that's where the money is. When we go to our medical hospitals, that's where we want to know something, what we want to know from our diseases. These kind of things, for example, will help to detect even what we say as very sensitive signals. Because the limitation so far was the best equipment that you have is what we say as the zero energy. So if you can go beyond or below, then there's a potential that you can actually go to unexplored territory. Right, another thing that recently that has been discovered is you can do this kind of experiments with artificial atoms. So instead of taking these Rydberg atoms or whatever atoms you want, you can now mimic or simulate these kind of atoms by using superconductors. Okay? So you come up with superconductors, and in this case, this paper, very recent, 2016, they managed to show that by coming up with so-called artificial atom, it reproduces the result that I've shown you previously. These were coming from the previous actual atom, but by using superconducting technology, you can also come up with what has been predicted previously. So the positive thing about this is you can manipulate, okay, the result without having to deal with actual atoms. So this is one other thing that we can do for playing around with the vacuum. Now, quickly I'm going to say that why we want to talk about the quantum computers. Well, if you look at the comparison here, you will talk about a quantum system replacing classical bits with what we call as quantum bits, or qubits for short. So, if you look at the second bullet, qubits follow the superposition principle and can exist as 0 and 1 at the same time. Okay, normal way of doing is we treat classical bit 0 or 1. 0 or 1. But for quantum bits, we have 0 and 1. Superposition. Okay, so I'll now give you just a taste of why the Quran is a miracle. Allah says in the Quran, Surah Al-A'la, ثُمَّ لَا يَمُوتُ فِيهَا وَلَا يَحْيَى. You will see them in the hereafter, neither dead or alive. So if you can reconcile that idea, 0 and 1, neither dead or nor alive, these kind of ideas can help us to become closer to the Creator, not away from the Creator. There are many other things that are unsolved as being said in the Quran. So this is one of them. So to be able to prepare quantum states in 0 and 1, we call it superposition, or the basic element of quantum information, the qubit, allow us to do SIMO, single input, multiple output computation in parallel. So what can we do with this? How can we harness this so powerful thing? Is, if you look, but before I go into that, we make quantum algorithms to program these quantum computers. So I really look forward to both our institution, particularly in IIUM, Malaysia, and IBA, Sukkur, to prepare the bright minds to be able to face the new challenge. Don't forget about being followers. The time is now for us to become leaders. Right? The thing is, if you wait for quantum computers to come and then you start to learn your principle and then how to program it, you are too late. But I think now is the right time. At least we need to know the principles. So, what can a quantum computer do better? So, number one, searching big data. Just imagine, SIMO. You compute in one go. Number two, designing better drugs and new materials. Machine learning, cryptography, just to name a few. So the potential is there. And when I conclude, I want to convince you that we cannot wait any longer. So this is the pictorial aspect of how to appreciate these quantum bits or qubits, the essence of building block of quantum information. On the left here, sorry, on my right, so on the left is the classical bit, 0 and 1. But here, for the quantum bit or qubit, you have an infinite way of representing 0 and 1, 0 and 1. All the points on the sphere, we call it the block sphere. These are the possible states to represent even a single quantum bit. So you can imagine, if you are able to realize these quantum computers, it will be a great risk, especially for conventional electronic transaction. Whatever you have, the public key cryptography will be gone in almost a jiffy. Mathematically, we can represent these various gates. We call, in this example, I'm giving you single qubit quantum logic gates, and it operates on state vectors. For example, here, for this phase gate, if you represent 0, is the vector 1, 0. So if you operate P onto 0, you get 0. If you operate P on 1, you get 1 times I. So mathematically, that is well represented. So these are examples of Pauli gates, Hadamard gate, phase gate. Now, the latest thing about middle of last year, how they actually couple this new idea of making the vacuum to be a friend instead of an enemy, particularly for quantum computing, is the heading of this particular write-up is quantum computer could simulate beginnings of the universe. So the question was, for many, many years before this, if we are not able to realize a large-scale quantum computer, what can a smaller scale quantum computer do? So this is quite a major breakthrough because these scientists in Austria managed to show that with a small number, particularly 4 trapped calcium ions, driven by a laser, it can actually become a real quantum simulator on how to actually explain the interaction between virtual particles when they're actually interacting. The normal way of actually explaining this kind of interaction is the gauge theory within the standard model. But what they have done is can also be proven by using classical computer. Okay, so that is good news, simply because by testing out this small-scale quantum computer, it has been able to prove the calculation that can be done classically. But what's the added value here? You can actually go beyond, simply because in physics they have this characteristic called entanglement. In supercolliders like those in Geneva, you cannot actually measure the entanglement between these virtual particles. But this can be done. Okay? So this is one example where you have how to harness the vacuum for quantum computing. Now, this other one is actually another interesting title, colors from darkness. Darkness means the vacuum. How can you get colors from darkness? I already explained. So the people in Finland lab managed to show that they can turn what we call as virtual photons into real photons. Okay, so from darkness, from emptiness, to something that's colorful. So the idea is very simple. If you put the 2 mirrors that we talked about just now, Casimir effect, and you make sure that one of the mirrors, okay, can actually, the thickness of this particular mirror can change abruptly. So we know that the speed of light may change because of the index of refraction. So by changing the thickness of this mirror, whatever virtual photon that is trapped in between the 2 mirrors will be able to bounce with extra energy. So these virtual photons that get this extra energy from bouncing from this changing thickness of mirror is converted into real photons. So again, it comes back to that paper I showed to you. People now, the scientists have found a way, instead of dealing with real atoms, they can now play around, for example, in this paper with superconductors to mimic elements that make up on the building blocks of quantum computers. So from virtual photon from nothingness, you come up with something that's real. So you can actually translate this into quantum bits. Right. So 2 more slides to conclude. This January 27 article just reaffirmed the previous experiments were in the frequency domain. Now this discovery, you can also now play with the time domain. So you can have the spatial temporal behavior instead of just looking at the frequency domain. And lastly, if you look at the January issue of Nature, you will see that 2017 is a big date, especially for Google and Microsoft. Okay, so Google is now pumping a lot of money to go superconductor, to realize the quantum computers. On the other hand, the Microsoft people, they are exploring a new part of quantum computing called topological quantum computing. And of course, the startups and research labs in all these advanced countries are also doing a lot of things to make sure that something is happening this year. Right, thank you very much.
Thank you very much, Prof, for your great ideas. You are welcome for the questions, please. If you have any question, you may ask. Please.
Thank you for this wonderful talk. My develop the things that you have invented. There is something really paradoxical about this medium effect actually, from a mathematical perspective. For example, when you try to compute sort of energy density between the Siegelian plates, you need to compute the zeta function at some negative values.
Yeah.
And so you come up with a series. And when we mathematicians look at those series, for us those are divergent series. But I never understood that how come the physicists are giving sense to those divergent series. So maybe I thought that it's a kind of a good opportunity for me to clear up this.
I think there's no real way to reconcile mathematicians and physicists. Physicists are somewhat stuck between mathematicians and engineers. They try to get an answer how to deal with these divergences. And as I said in the presentation, they resort to something like what you call renormalization.
Thank you very much, sir, for your great speech. And I want to know from you that since we have quantum computers, and how can these quantum computers help us to visualize the state of a star, like a neutron star said? How can we analyze some state of a star using this computer? How these computers help us to understand the stars?
Okay. So if you look into the literature, the existing famous algorithm for quantum computing are the ones that look a search algorithm. So you can do ultra fast search using quantum computers. But on the other hand, any nation state that comes up with the first workable quantum computers, that will be disruptive. So you need to have a defense. A defense, just like fire with fire, you must have quantum cryptography versus quantum computers. Two examples.
Question, please. Sir, you said that there is some fluctuation in vacuum. From where this fluctuation comes? Do we know about this? Existence of these fluctuations, from where this fluctuation, what sort of behavior was, something there was from where these fluctuations observed?
Yeah.
So what is the nature of this fluctuation, from where they are derived?
Yeah, I've tried to explain